Imagine a typical highway on a hot summer afternoon. The stream of cars, the heat, the wind shivering on the asphalt road. And through that stream moves a long silver tanker. Inside it sloshes 30 tons of gasoline. Every driver beside it instinctively feels a slight tension, a thin metal shell holding so much fuel. In essence, something like a wheeled bomb is driving right beside you. Inside its tank is a vapor mixture that could ignite with a single spark. Yet we almost never hear of a tanker exploding in the middle of the road. Every day, thousands of these trucks travel across the world. They supply fuel to cities, pull into pumps, and even face accidents. Yet they don't explode. And here arises the question that breaks all common logic. Why is a half-empty tanker actually more dangerous than a full one? What invisible enemy hides in the empty space above the fuel? And why do engineers fear it even more than the gasoline itself? Where does the spark come from with no fire or match nearby? Can fuel ignite all on its own? And the biggest question, what must come together for this moving bomb to work? And why is that combination almost impossible? Even if you deliberately tried. For a tanker to explode, 3 conditions must be met at the same time. And from the first screw to the last, the entire tanker is built so that this combination never happens. In this video, we'll break down each condition one by one. Now let's climb inside the tanker. Before we understand what an explosion is, we need the answer to a simple question. We think gasoline itself is explosive, but liquid gasoline doesn't explode on its own. Drop a lit match into a puddle of gasoline, and it will likely just go out. It's not the liquid that burns, but it's vapor mixed with air. Gasoline vapor only ignites within a very narrow range of concentration. Below 1.5% vapor in air, the mixture is too lean. There's nothing to burn. Above 7.5%, it becomes too rich, and oxygen runs short. Ignition is possible only in that narrow band in between. Think of a wood fire. Too little wood won't burn, too much smothers it out. The same thing happens with gasoline vapor. Every fuel has its own flash point, the temperature at which it starts releasing enough vapor. Diesel's flash point is about 60 degrees Celsius, so diesel doesn't easily catch a spark, but gasoline's flash point is about -40, meaning it gives off vapor almost constantly. Winter or summer, gasoline is always ready to ignite. So the entire history of tanker safety is really a history of the fight against gasoline. Inside a full tank, very little empty space remains above the fuel. In the heat, that small space quickly fills with vapor. The concentration climbs past the danger limit. The mixture becomes too rich. Even a spark brought close changes nothing. Without oxygen, there's no chance to burn. A full tank holds immense energy, but under normal conditions, releasing it is nearly impossible. And here's the first paradox. What happens when the fuel runs low? When a tanker unloads and becomes half empty, the situation changes. Now a huge empty space opens above the liquid and air is drawn inside. The dense vapor cloud thins out until it reaches the danger zone, so a seemingly empty tank can actually be the more dangerous one. Experienced drivers know that a freshly empty tank demands the same caution as a full one. Engineers understand this trap, so keeping air from freely entering is their first line of defense. A tanker is never box-shaped. It's always oval or cylindrical. This shape lowers the truck's center of gravity and reduces rollover risk. The curved walls withstand pressure and absorb the impact of the liquid. When braking or turning, 30 tons of liquid slam against the walls with tremendous force. To handle this force, partitions are installed inside the tank. 56 solid partitions divide the tank into separate compartments, keeping different fuels from mixing. Inside each compartment are perforated baffle plates. Fuel slowly passes through the holes and the waves break, losing their energy. This keeps the truck stable even during sudden maneuvers. But these partitions have another job, less obvious, yet directly tied to dangerous vapor. Because the tanker's real invisible killer is static electricity. Pumped at high speed, gasoline rubs against the tank walls and builds up charge. Just like when you pull off a wool sweater in winter and hear sparks crackle. Now imagine that same effect on the scale of tons of liquid. The charge builds up, and if it discharges into the vapor cloud at the wrong moment, disaster is certain. The baffle plates slow the fuel, reducing friction and static buildup. But that alone isn't enough. Defense after defense has been built against static. The first step, attach a grounding cable before loading or unloading. The stored charge flows calmly to the ground through this cable, never creating a spark. In modern systems, if the grounding connection isn't reliable, fuel transfer won't even start. After loading, there's a waiting period until the charge fully dissipates. In the most extreme cases, the oxygen inside is replaced with nitrogen gas. Without oxygen, the dangerous concentration window never forms, no matter what the spark. The second defense, a change in how fuel is loaded. Fuel used to be poured from the top, creating more friction and more vapor. Now it's filled slowly from the bottom through a sealed connector. Less splashing, less static, less vapor, less risk. But as fuel pours in and air is pushed out, the question remains, where does the vapor go? The modern answer is the vapor recovery system, a closed loop. Through a separate hose, the vapor flows back into the tanker, never escaping into the air. The same cycle runs when you fill your car at the gas station, but a tank can't stay completely sealed. The fuel itself needs to breathe. As temperature changes, pressure changes, so a vent valve is essential. But this breathing path is also an opening where fire could enter. So engineers created a marvelously simple device, the flame arrestor. Inside, thin metal plates, or mesh, vapor passes, but fire is snuffed out, just like the safety lamp that saved miners 200 years ago. Too much pressure is danger, too little is danger too, from both sides. A thin-walled tank can collapse at pressures close to atmospheric. So the tank carries two safety valves. One releases pressure, the other lets air in. Around the clock, these two valves balance the tanker between two dangers. An accident can start a fire, but fire and explosion are not the same. Spilled fuel burns in the open. Without a perfect mixture in a confined space, there's no true explosion. That's why emergency shutoff valves sit at the front left corner, findable even by feel in the smoke. Quick disconnect couplings seal the fuel lines instantly, but the weakest link in this entire safety system is a human being. The grounding cable, the valves, the loading speed, all of it is controlled by people. Most major accidents aren't technical failures. They come from haste or negligence. Remove just one of the three conditions, and no disaster occurs. 30 tons of gasoline passes beside you, and it's just cargo, not a catastrophe.